Okay, back again. And for our third segment, we'll pick up with the next example. Uh, this is about vertical motion of a baseball. Sometimes when the batter hits the ball, it pretty much goes straight up in the air and comes back down right where it was hit. And if he doesn't step out of the way, he's going to get hit in the head with it. So this is one of those situations here where the batter basically hits the baseball straight up in the air when he's up at bat, and the catcher catches the ball 5 seconds later. And in other words, the batter steps out of the way and the catcher steps forward to catch it. So we're wondering a few things here. What is the initial velocity of the baseball when it leaves the bat? What is the maximum height that the ball reaches before it starts coming back down again? How much time does it take to go from the bat to the maximum height? What is the acceleration of the baseball at the maximum height? And what is the velocity of the ball when caught? So there are a few things that we need to realize and assume about this situation before we can actually address it. First of all, we're assuming that the height at which the ball is hit by the bat is the same as the height at which it's caught. We could make those heights different if we wanted to, but it would be simpler to make them the same, and that seems plausible enough that they probably really would be about the same. And we'll call that y original, and we'll call it 0. Y original is equal to 0. We also assume that the ball is caught in the same spot that it's hit in terms of the XY plane, left, right, forward, back. Because if it's not, then what we have is ballistic motion rather than free fall, rather than pure free fall. So it basically, in other words, it literally went straight up and straight back down again to the same spot. And as usual, we're assuming that positive is upward and negative is downward, so that we can use the equations that we've been given without having to change them around any. Okay, so for part A, what is the initial velocity of the baseball on leaving the bat? The best equation to use would be the one that solves for the final location in terms of up and down. And this is kind of a reminder that you don't always choose the equation that is solved for what you're looking for. Sometimes you, in fact, very often, you have to look at what's in the equation and choose the equation for which you know everything except one thing. Okay, so for this equation, we know the final position, that's 0, because the ball comes back and is caught in the same position where it started from. Y original, again, would be 0. V original, that's the only thing we don't know here. The time, we know the time, 5 seconds. We know the acceleration due to gravity, 9.8 meters per second squared, and again, we know the time. So we have to solve this equation for V original, and we can do that oops. First of all, you have to get V original alone. And so that means basically get everything else on the other side of the equation. The terms that are added or subtracted are the easiest ones to do because you just take them over to the other side and change their sign. So we can subtract Y original. Okay, and that equals V original T plus minus 1/2 GT squared. Okay, again, we're still looking to get V original on it by itself, so we can basically add 1/2 GT squared to both sides. Okay, and that should equal V original times time. Then if you divide by time, we get V original by itself. So we should end up with this equation here. And that, in fact, is what I ended up with. Okay, so we put in the things that we know. Y final is 0, Y original is 0, and it's going to be plus 1/2 GT squared now because we took the minus 1/2 GT squared over to the other side of the equation. So it's plus 1/2 times 9.8 meters per second squared times 5 seconds squared. Don't forget to square the 5 over 5 seconds. And that turns out to be 24.5 meters per second. So that is our velocity upward. It's positive, again, because it's upward. Okay, so what was the B? B, what is the maximum height reached by the ball? In this kind of motion, remember, the ball is going straight upward, and as it goes upward, it's going slower and slower and slower, and eventually it stops and turns around and falls back to Earth. That means at the maximum height, the velocity is 0. And that is very useful information to know for the purposes of these equations, because that fact is how we're going to find the maximum height. So if V original is 24.5 and V final at maximum height is 0, then we can put those numbers in for this equation. V final squared equals V original squared minus 2G Y final minus Y original. And YF is just going to be the maximum height at this location, the maximum height in this part of the problem. Okay, so we basically solve for YF. We end up with VF squared minus VO squared over negative 2G equals YF minus Y original. So if you add Y original to both sides, you get negative VF squared minus V original squared over 2G plus Y original equals YF. And again, YF for this part of the question is going to be the maximum height. V final, again, the velocity at the maximum height is 0. The original velocity was 24.5 meters per second. And that's over 2 times G, which is 9.8 meters per second squared. Plus 0, it gives us Y final, and that's 30.6 meters. That's the maximum height. C, part C, how much time does it take to get to the maximum height? Well, in projectile motion, and actually the free fall situation where something is going straight up in the air and then falling straight back down again, that is a type of projectile motion. And projectile motion is symmetrical, meaning, for one thing, that it should take an equal amount of time for the ball to reach its maximum height as it takes to come back down again. So in other words, if the total time up and down is 5 seconds, half of that time should be spent rising, and the other half should be spent falling. So in other words, the time to reach the maximum height should be 2.5 seconds. So you can answer that question with logic, like I just did, or you can do it mathematically. The time to reach the maximum height is the time when velocity is 0. So to use that, you can just use the equation final velocity equals original velocity minus GT and solve for T. So to get T alone, you have to take V original over to the other side. So we get V final minus V original equals negative GT. And you can divide both sides basically by negative G, and that solves for T. So negative V final minus V original over G is T. V final at the maximum height is 0 minus 24.5. Take the negative of that and divide by 9.8 meters per second squared for gravity. And it gives you the time, and look where it comes out to be, 2.5 seconds. So it's true, it did spend half of its time rising and half of its time falling. For part D, the question was, what is the acceleration at the maximum height? And that's a tricky question because the velocity at the maximum height is 0. And so you might tend to assume that if the velocity is 0, the acceleration must be 0 also. But that's not necessarily the case. In this case, the ball is subject to acceleration due to gravity all the way up and all the way down. So the acceleration all the way up and all the way down is negative 9.8 meters per second squared everywhere, even at the moment it stopped. Okay, so 9.8 meters per second squared downward, or negative 9.8 meters per second squared. E is asking about the velocity when the ball is caught. And this is another one, another question where you can answer it logically or you can answer it with math. And it should work the same either way. Because projectile motion is symmetrical, the velocity on landing should be the same as the velocity on takeoff, only in the opposite direction. So if the velocity on leaving the bat was 24.5 meters per second, the velocity on being caught should be negative 24.5 meters per second. Seems logical enough, and it is, because when we do it mathematically, we can use the equation V final equals V original minus GT. And this time we're using the equation for the entire period of 5 seconds. And V original then would be 24.5 meters per second. And that will be minus G, which is 9.8 meters per second squared, times T, which would be the total time. And let's get rid of this because that's confusing there. Total time is 5 seconds. You end up with 24.5 minus 49. That's negative 24.5, which is exactly what we thought it was going to be. So there you go. Projectile motion is indeed symmetrical. It's so symmetrical that even if you took, like, what is the velocity of the ball when it's 1 meter above the bat? And then you take the velocity on the way down when it's 1 meter above the catcher's glove. And they should be the same except for the sign. And it should be the same, throughout the entire process. An example that's a little more involved is basically a rocket booster being shed by the rocket. And this is example 316, where you have a rocket with a booster that takes off straight upward. And at a height of 5 kilometers and a velocity of 200 meters per second, the booster is released. Sorry. So what we're wondering here, what is the maximum height of the booster? In other words, oh no, sorry, that's not at what height is it released, because they told you that. The maximum height of the booster is actually not 5 kilometers, because remember, the rocket is moving upward. And so at the moment the booster is released, it still has that upward momentum. So the booster is going to continue rising. Oops, it's going to continue rising a little bit more before the pull of gravity causes it to stop and start falling again. So the maximum height of the booster is actually going to be a little above 5 kilometers. So we have to see how far above. And then we also know, what is the velocity of the booster at a height of 6 kilometers, neglecting air resistance. Okay, by the time you're that high, the air probably isn't much of a factor anyway. So that wouldn't be too bad to try and ignore that. Okay, so for our setup, we're going to call upward positive and downwards negative. we're going to set the point at which the booster is released as 0 in terms of y. And we, of course, since this is a case where the booster is rising and then it stops and then it falls, the maximum height of the booster is going to correspond with 0 velocity. So for part A, what is the maximum height? It would be best to use the equation final velocity squared equals original velocity squared minus 2g times the displacement in the y direction and solve for y final. Because we know that the final velocity is going to be 0. That is, the velocity at the maximum height is 0. And we know what the original velocity was, 200 meters per second. And we know what g is. So we take this equation and solve it for yf. We end up with negative vf squared minus vo squared over 2g plus y original. And we know all of those things. So negative 0 squared for final velocity is 0 squared at the maximum height, minus 200 squared, that's the original velocity, over 2 times 9.8, that's gravity, acceleration due to gravity. And y original was 0, so I didn't even bother writing that. That comes out to 40,000, sorry, negative. Oh, right, okay. It's positive because you got a negative and a negative. So I thought I dropped something there. But no, 40,000 divided by 19.6, that's 2,040.8 meters. And that is, okay, A, what is maximum height? This is 2,040.8 meters above the point at which the booster was released, because remember, we took the point at which the booster was released as 0. So that's 2,040.8 meters above the 5 kilometer point, or in other words, 7.041 kilometers total. Because 5 kilometers is 5,000 meters. You add 2,040 to that, that's 7,040.8 meters, or 7.041 kilometers. Okay, B is the velocity of the booster at a height of 6 kilometers. We know from part A that the maximum height is 7.041 kilometers. At that point, the velocity will be 0. At 6 kilometers, you're 1,000 kilometer, or you're 1,000 meters, or at 6 kilometers, you're 1 kilometer or 1,000 meters above the point at which the booster was released. So the booster is still rising because it's under the maximum height, but it should be slowing down. So we can basically use some logic to check our answer to see whether it seems reasonable. So the speed of the booster, velocity of the booster at this point at 6 kilometers should be less than 200 meters per second, but it should be greater than 0 because it's 0 at the maximum height and it hasn't gotten there yet. So like I was saying, the altitude of 6 kilometers is 1 kilometer or 1,000 meters above the point at which the booster is released. And we've set that point, the point of release, as 0. So the height of the booster for part B will effectively be 1,000 meters, 1,000 meters above the 0 point. So if y original, that is the point at which the booster is released, is 0, and v original is 200 meters per second, then we can take the equation v final equals v original minus 2g times the displacement in the y direction, and just basically put in the numbers. V original is 200 meters per second squared minus 2 times G, which is 9.8, times Y final, which for this part of the question is 1,000 meters, minus Y original, which again for this part of the question is 0, because we took the point of release as being 0. And that ends up being 40,000 minus 19,600, and that's 20,400. And you might notice that that is way greater than 200 meters per second, when we thought that it was supposed to be less than 200 meters per second, because the booster should be slowing down once it's released. And the catch is, don't forget that this is V final squared. So then when you take the square root of 20,400, you get 142.8 meters per second. That makes sense. That's smaller than 200 meters per second, so it is slowing down, but it's greater than 0 because it hasn't come to the maximum height yet. Of course, the solution to a square root is positive or negative, but in this case, it should be the positive number because the booster should still be rising at a height of 6 kilometers. It doesn't start falling until 7 kilometers, at which point the velocity could be considered negative, but it's still going up. And so at this point, and well, actually, it's assuming that it's 6 kilometers on the way up, it would be positive 142.8 meters per second, but it's going to pass the 6 kilometer mark again on the way back down. And again, because ballistic motion is symmetrical, that means that the velocity would be negative 142.8 meters per second when it passes 6 kilometers on the way down. So you can actually use both of those numbers as answers in this question. Okay, if we come to the next section, which is velocity and displacement from acceleration. And I think I'm going to leave this for class on Monday and Wednesday because we're getting close to the end of the chapter. And we went over on the first 2 segments of the video, so I think I'm going to cut it a little short on the 3rd one. So you're welcome. See you in class, hopefully.